Yep, it's William Wallace's soul. Wait, Marcellus Wallace's soul. William Wallace was Braveheart. Not that Braveheart, the Scottish Braveheart. Not a Braveheart that's sort of like Scottish, but like Mel Gibson, but less anti-Semitic. That reference. And now I have to put the friggin' machine back in here, because all I have in here is 2 lights. Alright, so all jokes aside, it would be charitable to call that a joke. Here is the actual reveal of the contents. And this package, well, I say package, this case had a UPS shipping label, and you can see it had others before me. I took mine off so you don't see my address, but yeah, the eBay seller just sent this to me in this crate, which is fine because there was this giant piece of foam with another piece of foam underneath that, and then 3 more pieces of foam stacked up on top of here, including one that was form fit to this opening. I took those out because those were just massively in the way. And as you know from the title of the video, this is an EMC NSG 200E. And NSG 223A, which is a Bedienungsanleitung. Nope.
Bedienungsanleitung Steuersimulator.
Thank you, Google. Or a manual interference simulator.
Manual Interferenz Simulator.
And the reason there are 2 manuals is because one is for the unit itself, the mainframe, and the other is for the module that goes into it. This is really more module. Well, I'll show you. It's more module than mainframe at this point. Also came with some fairly knackered cables. And this entire thing, according to the UPS shipping label, not this piece of equipment, but this is heavy, but the entire thing with the case shipped at 59 pounds. Nah. So I'm going to get the case out of the way because it's just been taking up space in my basement anyway. And we'll look at the unit. And there we go. The NSG 200E is the mainframe, and the module is NSG 223A from Schaffner in Switzerland. And an interesting side note about this is that this was owned by the AT&T Capital Corporation, which I'm guessing is a corporation that AT&T formed to own equipment, like capital equipment. Not too familiar with AT&T, but also all these no calibration required stickers are from AT&T, and presumably so are these inventory control stickers. You can see it's labeled 110 volts. This is obviously made in Europe, so it's usually meant to work at, I think there's an older unit, so maybe 220 volts. If you just find one of these on eBay, there's a very good chance it'll work at European voltages, either new or old European voltages. But this is made for the US market, well, North American market, as you can see from this socket. So as you might have guessed from the manual of the manual interference simulator, this is for creating interference on an AC line for testing filtering, spike protection, surge protection in upstream devices. This machine is kind of dangerous in that it's capable of emitting 3 kilovolts max for asymmetric noise on a waveform. I didn't buy it for that, but I did buy it to simulate lesser spikes and interference on an AC signal. And fortunately, it has a pulse amplitude dial, which goes from 0 all the way up to 100, and that's by percentage. So if it's at the 1000 volt symmetrical range, 100% would be 1000 volts. If it's at the asymmetrical 3 kilovolt range, 100% would be 3 kV. So therefore, if we, let's say, had it set to the 1000 volt range and had it at a nice, polite 5% or so, we should see 50 volt spikes. It also has a section to control triggering, and we'll get more into all the details of it. For now, let me show you the back. I did cheat a little, and I opened up the box before I did that whole spiel, looked at the manual, and it's heavy because, amongst other things, it has a variac inside and at least one other transformer. So the back is very simple. We have an input for the unit itself, meaning the electronics within here. That's what this powers. This powers the test fixture, And so the line that goes into this comes out the front of the unit and has any interference added to it that you might specify using the controls in the front of the machine. It also has a couple of extra ground points. The manual does reference at least 2 earth connections, I suppose one being the pin here, and then having an extra earth connection, which I guess would be 3, because both of these would be earthed. Although you might have your test supply input connected to a generator or something. And this says 250 volts AC max or 50 volts DC max, although the manual does specify a certain condition where you can input up to 400 volts DC. But my plan is to primarily use this with 120 volts, which is the standard line voltage here. Well, kind of. See my other video. And it can handle up to 16 amps of current. And interestingly, this does say the input is universal mains, 100 to 240, 50, 60 hertz. This is a bit of an older unit, so I thought this would have a voltage selector switch on the back, but I guess not. It does have that 110 volt label on the front, and it did come from AT&T, so I should imagine if it did need to be set up, like if there were transformer taps that need to be changed, it is set up for 110 volts right now. But before we power this up, I do want to open it and look inside for a couple of reasons. One is that when I took it out of the box and I kind of turned it on its side just so I could carry it away, I heard something rattle and sort of fall through the inside of it. It sounded very small, possibly metallic, but hard to tell. If it's metallic, that obviously would be a huge problem because this is a high voltage device. So shorts in here would definitely not be a good thing, or even near shorts, because you could get arcing. Second reason is I just want to check for any obvious loose connections, deterioration of components. For that same reason, high voltage, don't want to mess around with it. Also, this ear looks like it's canted in more than this one, but they both are, and I think that might be how they're... I can't imagine. I thought they should be straight. So I'm afraid this thing might have been dropped or abused otherwise. And from all those shipping labels, this has definitely been shipped across the country, at least a few times, for many years. So it's probably taken some use and abuse. Although, as you saw before, the front panel is in very good condition. All the buttons seem to work, and all the pots seem to turn smoothly. So it doesn't seem to be anything mechanically wrong with the front of it. And the back, there's not much to it anyway. And fortunately, this manual is in both German and English, at least fortunately for me. Front half is in German, and the second half is in English. And I'm not going to go through the entire manual, but I did just want to look at the block diagram. It shows the 2 mains inputs, the test supply, obviously, and the simulator supply, which is the supply for the device itself. So the simulator line goes into the power supply, logic circuits, which are controlled by, well, the control. And the logic circuits are electrically isolated from the interference generator, which consists of a variac supply 0 to 1000 volts DC for the spikes, a capacitor to charge and then release for the spikes, a thyristor, which controls the release of the capacitor, which then goes through the rise time and polarity control, and then to the asymmetric or symmetric output switch. And then the output of all that connects to the test supply line. And so the test supply comes through here, just goes through here, and then straight to the test supply out, but is just coupled to this circuitry that generates the interference. So overall, from a block diagram perspective, very simple. In fact, it's not a very complicated device as it is. And I will just leave that there for a second so you could pause on it and read it till your heart's content. Unless you're on a phone, in which case it might be too small to read. And I'll also get the operating controls section in here so you can pause and read through it if you wish. And so I'll reference the manual when appropriate as I go through the device and show it to you, but let's just dive into the actual thing itself rather than looking through this. So I said before, this thing is more module than mainframe because this is the module. And it actually came with a bunch of screws loose or hanging out. Like, I didn't unscrew that one. So that's a bit of a concern, because this was sold as working, but, you know, it's eBay, so you can't be absolutely sure. And then, I tried pulling one of these, but there's no, like, pull handle to pull the module out, but the module actually does go to the back of the unit, so you can push it out from the back. Oh, that's an unpleasant noise. And we have this beefy connector in there. Presumably a relatively high voltage, definitely high amperage looking connector. And the module is completely enclosed. I mean, vented, but enclosed. And yeah, the mainframe, just, there you go. So I guess it comes out to here. So it's about half and half, to be fair. And here is the other side of that connector, which looks very familiar to me, but I don't know what it's called offhand. And this, oh yeah, and I was going to say there's some information on the back, but since the module goes all the way through, that's the information we already saw on the back. There is a calibration sticker, but it appears to already be broken, so no harm done if we open this up. And also, does this just slide right out? Because this doesn't seem to be pushed all the way in. There's a little gap there. So it seems like it would slide out, but I guess not. It's very dirty in here too. So maybe I do have to take off the back panel first. And I feel like you know it's an older unit when it uses flathead screws. And they're very narrow bladed flathead screws. Starting to doubt that this back panel even needs to be taken off. A little corrosion on the end of that screw. That's not good. Yeah, because there is something screwed to this back plate, so I don't think that's just going to come off. But maybe that'll give us enough leeway on the sides to get this top piece to move. Inelegant, but oh yeah. There we go. Should come free now. Excellent. Yeah, I didn't need to take the back off, but definitely need to loosen these side rails. And yeah, the back is screwed onto this transverse plate and also this power resistor. So up here, this dial is the percentage of voltage that you want to give to it, percentage of 1000 volts or 3000 volts. So it's a variac. Ooh, and that's also another way you know it's old. Made in West Germany. Based on the fact that this Schaffner part is potted, this may be the high voltage transformer. So I don't think that variac isn't going to run at 1000 or 3000 volts. That's probably just pre-scaling the voltage that's going into, I would guess, this transformer. This board here is the switchboard for the front switches. And it looks like those switches just use resistors and capacitors to set the various parameters, which are refill-looking caps, but they all look like they're in good shape. This one, oh. Actually, there is one underneath there that has a bit of spiderweb cracking on it. And this support here, there's a hole there that's like missing, I don't know, maybe a rivet or a post. No, it was a post with a nut on it. This transformer's got a fuse in line. And then along the side here, a bunch of logic circuitry. So from the block diagram, that's the logic, I guess, that it was referring to. And I thought that this logic board would be isolated inductively, maybe through a transformer from this side, or maybe there are opto-isolators in there, but I don't know. Kind of curious to dig into this thing a little further. It's not like hugely complicated, but we at least have a block diagram to get us going as well. But I do kind of want to power it up too before I take it apart, just in case I mess something up. So other than maybe one of these reefa caps, maybe a couple of these reefa caps looking like a little sus, but not completely. Oh, actually, this one is just cracked on the top. That's not good. Oh, these big caps actually have a discharge resistor across both of them. It is well designed though, and I like how this support plate here is both a support for some of the components on this side, but it also goes top to bottom to act as isolation between the high voltage side and the low voltage electronic side. But yeah, both these big caps look good. Nothing looks blown up. I don't see anything scorched or charred in here. There's no signs of an electrical disaster. So, and whatever was rattling around wasn't in here, I don't think. You know, I'm just realizing when I heard something rattling around, may have been the fact that a couple of these were loose. So that might have just been, you know, doing that. Oh, it sounded like it was coming from in it and it fell farther than just that, but maybe I wasn't paying enough attention. I'm going to open up the mainframe as well, so we'll see if it's something in there. Okay, but for now, this part anyway doesn't look too scary to power up. So I'm going to close this up for now. I think I will do a more robust investigation of its internals after we test it out. It is good when you have the right size flathead driver, though. The screws just capture really well. Alright, let's dig into the mainframe. I took a break for a couple of days from this project, worked on another project. The inside of this had dust all over it, and like metallic dust, because couldn't get it off my fingers. I actually got some on the walls of my bathroom when I went to turn on the lights before I washed my hands. Yeah, it had that, you know, metallic, tangy smell. Not tangy, you know what I mean. So I'm going to take a cue from Marco Rep's handbook and do a full rectal exam.
Black nitrile gloves.
He usually wears these to keep the oils from his fingers off of the very sensitive electronics he works on. This is not so sensitive in that kind of way anyway. So I'm just wearing these for hand protection, so I don't have to deal with having that crap all over my hands later. In case you're wondering why I'm wearing them. When I went to put this away the other day, though, I did try to screw this module in, and most of these will not screw in. They're just loose, or they won't catch threads anyway. This one did, but maybe that's why they were all kind of hanging loose when I was looking at it before. Yeah, so I thought it was just maybe a lazy engineer. Let's move this out of the way for the time being. Oh. No wonder they couldn't catch the threads. Alright, so, yeah, this is why I wouldn't catch any threads on some of these, is because these are little threaded inserts that can slide back and forth, and these red plasticky, rubbery rings, yeah, they're plasticky, they're pretty hard plastic. I think those are intended to hold those inserts in place, because otherwise they can just slide around. And, yeah, they were just out of position. They're not very hard to move around, so maybe just as this thing was shipped around the country, they got knocked out of position. So, not a big deal. That seems like a real easy fix, so all I gotta do is figure out where they go, and then I can screw the front in. Nice. Interestingly, there are calibration stickers on here. I mean, 2 of them. And it does say calibration void of seal is broken, but on the front it said no calibration required. And regardless, even if this machine were in calibration at one point, which I'm sure it was, it's definitely not anymore. So, I still feel somehow guilty about removing, or at least destroying, calibration or certification or factory seal stickers, even though I do it all the time. I think this cover is let into the aluminum sides, though, so I don't think it's going to come off with just these 4 screws. Well, the calibration stickers would make me think that that is how you open this up. Because after all, why else would they put them there? Oh. Oh, it is kind of... Ooh. That's interesting. Yeah, it'll come out. It is inset into these rails a little bit, but I think with a little bit of flexing, yeah. I don't know if that's the approved removal method, but hey, that worked fine. Okay, now that's some old school looking stuff. Ooh. Are these enormous capacitors? No, I think... Are they capacitors or potted transformers? I think it's one unit. I thought that was... Yeah, let me zoom in on this a little more. Yeah, this is covered in a layer of fine dust. But I thought these were 2 modules. I think it's one module that's potted together. It's definitely potted. You can see that slightly uneven layer of potting compound on this top there, just glistening right over here. It's making me think it's a high voltage transformer, but I mean, these wires are very thin though, and they're very close to other wires, so if it is a high... Oh, this connector is loose. It might be loose intentionally though, so that the locator pins from this module kind of position it before this is set in. So I'm thinking that might be on purpose. I'm not familiar with these type of connectors, but it seems logical. Oh, this is also a switch right here. It's a not so micro switch. It's got a little blade that goes down between there, and when the locator pin goes into this top hole, it'll hit that switch. So I think that is our safety interlock, or at least one of them, for it knowing the module is in place. Can I poke that with a screwdriver? Ah, this screwdriver is just too short. What else do I have handy here? Maybe this zip tie will push it in. Yep. So if I insert a zip tie, that's sufficient to activate the switch. And that's an impressive transformer. I think that accounts for most of the weight of this, because this is quite heavy. It has one winding on top and one winding on the bottom. I'll take this apart later, hopefully, and we'll get a better look at it. And also very interesting is that the windings are actually very thick, very stiff metal. Looks like it is copper under there. I just scraped away a little bit of that solder. And of course it's dark brown because of lacquer. But yeah, this transformer is a beast. And this... what is that? It's labeled Schaffner RF529. Ah, okay. Well, this potted part, right off the bat, is labeled filter, and the part number printed on there is RF529. And that's actually in line with the test supply input, because here's the device under test output, and here's the device under test input. This input is for the simulator itself. And that does have its own filter and fuse. So simulator line input, fuse. I don't see a fuse, unless the fuse is integrated into... oh yeah, the fuse is part of the inlet. Alright, so that... and by the way, speaking of Marco reps, that's a Schaffner mains filter back there, needless to say. I mean, why would they put someone else's brand in there? And he had a problem with one of these blowing up and exuding sludge and stench all over his apartment, which I don't really care to have. I think that was in his flute calibrator video. I think the flute calibrator vomited. I'll let him explain.
These epoxy reefer Y-caps accumulate humidity, which leads to leakage currents, heat, and ultimately tar diarrhea being sprayed everywhere. I've learned my lesson. Now vintage Schaffner mains filters are on the same replace on first sight list as carbon composition resistors and electrolytic caps.
Yeah, that's what it was. So the fuse is integrated. I think, is that filter referring to the mains filter back there? Yeah, FN365 is the part number on that. So everything from here is just part of that receptacle. Then it goes to the main switch, then the safety plug-in switch, and then mains power goes to the plug-in module. And also over here, what is REL 1? I guess is a relay. Where is there a relay? Oh, this black unit down here is the relay. So mains voltage also gets split off to this relay and then to a switch across the mains coming in on this input. But I guess maybe that switch is indicative of part of the relay. So maybe the relay can toggle to either mains input. Seems weird. I mean, I'm sure there's a reason for it. We'll find out. Then S3 is somewhere. Then that goes through that filter. Then where's this giant transformer? Is that just... unless that's F765, that's part of the filtering. Yeah, the only marking on the transformer is 402212. So, yeah, I'm guessing it's an inductor, not a transformer, as I first assumed. Yeah, alright, so this is an inductor, not a transformer, I'm pretty sure. Because I think it's just used on each of the mains legs for filtering, as is this. We don't know what's in here. Maybe some capacitors and other inductors, smaller inductors. But I think this is just one giant fuck-off inductor. Because, yeah, the other thing is, both sides of this have the same thickness of, I want to call it wire, but it's really more of just like copper bar wrapped around. And it looks like the same number of turns, just based on the width of the windings. So I think it's 2 equal turns. And so I'm pretty sure it's for common mode interference. So yeah, it's an inductor for interference suppression. It's just a hell of an inductor. Which is, I guess, all of this, I suppose, is to prevent the back propagation of the test noise back into the mains power system. Which, yeah, I most appreciate. And that's why this would be common to all the modules that sit here, because any module in here will generate interference. That's the whole purpose of this entire system. Unfortunately, all my most sensitive equipment down here in the basement is on double conversion UPSs, so it should be relatively safe from transient voltages and noise. And the UPSs should protect against that anyway by cutting off the mains. So I'm not too worried, but I'm glad all this filtration is here. Let's just hope it's functional. And let's just hope whatever issue Marco Reps had with his tiny mains filter crapping out and vomiting all over the place doesn't happen in this immense unit where it starts gushing its potting resin and or smoking or exploding. So that's kind of the overview of the internals for now. These reefer caps look okay. Not fantastic, but I'm kind of willing to power this thing up and see what happens because I'm not observing any obvious shorts or any obvious pants or any real damage of any kind in here. So yeah, everything looks okay except for that one reefer cap in this module, but that could have just been damage to the plastic casing of the cap, although it's a reefer cap, so I shouldn't hang my hat on that idea. That went back in without too much issue. And before I slide the module in completely, I'm just going to make sure all of these dealies are aligned, at least as best as possible. The other red ring on this one, I think, has slid all the way over, so that's going to be dicey. Alright, hopefully that does the trick. The problem is this system is very jiggly. Like, these screws are long, so they jiggle around. There, we got capture on that one. Now that one oh wait, no, I did get that one. Haha. Alright, well 3 out of 4 ain't bad. I'm not exactly going to be moving this around violently, so that's fine. And you know what, I got this camera set up right now, and I think this is mostly in focus, so that in case it does blow up and emits magic smoke, we can get a nice wide view of it. Oh, and before I plug this in, I am going to be supplying my own power leads because this is a real thin and kind of old and nasty power cable. And this was bodged together by someone for the device under test input. You can see it's barely attached. I'm going to save this connector though. That's a useful connector to have, but this cable, not so much. Oh, and this cable as well. This has definitely seen better days, so I won't be using this one either, although it does have the high voltage connector on the end that I do kind of need, so I can always fabricate a new cable with that connector. This is a very high quality connector, also made by Schaffner. Yeah, very nice connector. Just so you're aware, plugs into those high voltage ports in the front. Now, this one suffered the same malady. I guess it's just this insulation got real brittle and just snapped. Has the same connector on the other end, by the way. One of these is a ground connector, so I suppose since they still do appear to have continuity, it would still be fine to use either one with a ground connector, but not for the 1 kilovolt, 3 kilovolt, or 5 kilovolt outputs, which can be toggled with this switch. So to start this up, we'll be putting this at 1 kilovolt, turn that all the way down, which should turn the variac all the way down and give us 0 transients. And I guess we'll start with it triggering at 0 degrees phase. We're going to use the internal. Yeah, okay. And the polarity, I guess positive to start. By the way, this electrical tape and the zip tie is not structural. That is just to label it. You can see it's got the same on the other connector, and on the cable it has other labeling, just to keep them unique. Okay, so the other end of this cable is plugged into a power strip, which is currently off. Oh, this requires the notch on top. I gotta get a different cable, actually. And nuts, what I realized is this has the little notch cut out in the top. This does not. And I don't think I have any handy with the notch. Let me just double check. I counted 14 cables I have with this style of connector. None of them have the cutout in the top. So that means I'll just repair this one real quick, or at least make sure electrically it's okay on the inside. Yeah, there we go. Oh yeah, okay. So yeah, whoever made this up, just left these leads too long when they stripped them back, and then they couldn't actually get the insulation under the cable retention. Electrically, it's fine. Alright, well, as long as there's no shorts in here, I'm just going to use it as is for now, because I kind of want to get this device powered up already. Alright, so again, I guess take two. We have now this cable plugged into here. On the other end of it is a power strip that is currently turned off. This is going to that same power strip. Alright, and I'm disconnecting the power from this unit for a second, even though I just put it in, because this does have a ground connector for the device under test right there. I just want to see if that actually grounds the entire chassis as well. Wait, surely it must. Because this... Wait a minute. Wait a minute. What? How is there no continuity between this metalwork? I guess this is coated aluminum? I don't think it's painted. Is it like anodized silver? It's anodized to be aluminum colored. Okay, what about this screw? Yeah, okay. Well, at least that has continuity. And then we should have continuity between this screw and, for example, this ground. Yep. And this ground. Okay. That's really what I wanted to test because, again, this ground is coming off of a completely different circuit here in the basement, closer to the panel. So this is a redundant ground, and I just wanted to make sure that we absolutely did have continuity to these grounds. So we should be all good now. And just because this thing is capable of putting out up to 5 kV in certain circumstances, the chassis should be grounded thoroughly, but I do want to, not live too much on the wild side when I'm powering it on for the first time ever, or for the first time in probably years. Okay, so this power switch is off, that power switch is off, so no power should go to the unit. However, like I said, I'm kind of worried about that mains filter in the back. So I'm going to flip on the power strip and see if anything blows up. Power strip is on. And the power strip, by the way, is a trip light isobar. So the power strip has surge protection and spike protection, at least to an extent. The power strip is plugged into a GFI, which does work because I accidentally tested it recently. And the trip light also has a circuit breaker in line. So, yeah, let's see what happens when we just power up not the test supply, but just the unit itself. Nope, heard a relay click as well. Yeah, I just realized there's no indicators on the front of this to tell you it's operating. There's just 2 line voltage indicators for the output. Any weird noises? Nope, no weird noises. It's probably a good sign. Any weird noises if I twiddle this knob? Oh yeah. Oh, there was ticking. Was it arcing? It didn't sound like arcing. No, it might be arcing. The problem is it was a very low noise and it's so loud down here in the basement. Let me just stick my microphone not dangerously close, but relatively close to the unit. Hopefully that got picked up on the audio. I don't smell any burning or anything, so that's, I don't smell any ozone either. It's probably good. Let's switch on the test supply. Why not? Are those very dim lights? Yeah. But one of them is illuminated, one is not. I mean, I know I have the test banana jacks, but it'll actually fit in better into this connector. That can't be good. Oh, there we go. Just bad connection. Okay. 121.7 volts. Oh, this indicator is actually glowing just very dimly, and you can only kind of see it from a lower angle. I'll show it off later. So I guess the next step would be to get an oscilloscope and see what it's putting out. Alright, so here's what we got going on. Handheld oscilloscope, battery powered, although I did forget to charge it, so it is plugged in right now. Going into channel 1 on the scope is this differential probe. It is made by MikeSig, right side up, and it's model number DP113. I don't know. It was relatively cheap. The differential probe is being fed by L1 and L2 from the test supply output. And I like how they provide these taps because, first of all, I mean, obviously it works great, and these are actually even shrouded banana plugs and shrouded banana jacks for extra safety. And if this is going to be 1,000 volts going into... This is rated for up to 1,000 volts, by the way. And we'll just have to keep this unit on 1 kilovolt max while testing with this setup. So I got a split screen going so that we can see the scope screen and we can see what's going on in the front of this unit, at least with these controls. Just gonna move these wires out of the way a little bit. I'll turn the power strip on, turn the device power on, turn the test output power on, and adjust my time base. And there we go. Now we got a mains waveform. Why is it clipping? What if I put the differential probe at 500x? Still looks like it's clipping. Is that the scope or is that the differential probe? Hopefully good enough to see transients. All right, now if I just turn this up slightly, what do we see? It's still getting that dangerous sounding clicking, which gets louder the higher I turn this up. Oh, and a loud pop. Okay. That probably didn't come out on the mic, but it did its usual click, 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 click in rapid succession, and then it went click, 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 pop, click, 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 click. So I think either something flashed over or a small cap blew up. Based on the sniff test, I don't think a small cap blew up. I think something arced. And the waveform looks fine, unless it's just... Oh, wait, there we go. Ah! It's a very quick transient, and it's not on every main cycle. Okay. And what if I twiddle with the phase knob? Does that... Yep. That moves it along the waveform. Cool. I think I need to trigger on channel 2 on the scope off of one of these. Let me check the manual. Well, the manual is fairly robust, although not physically because these pages detached, but hey, things start detaching from you when you get old. So we could see 9, 10, and 11 are those three BNC outputs on the front, and they are described thusly. 10 is a mains reference, positive at the zero crossing of the mains voltage. I think the one we want, though, is 9, which is a triggered output pulse, 20 microseconds when pulse is triggered. Negative flank, I guess, means 20 microseconds before the pulse is triggered. So then, as long as we have the time base set correctly, we should always see the pulse, as long as we're triggering on, in this case, channel 2. Switch on the unit again. So we have 5 volts per division on channel 2. It looks like it's at about 12 volts, and it's pulsing to 0. So we just need to trigger on that. And now, if we start firing some pulses, we should always see them. Oh yeah, right where that trigger is. Actually, what did it say? It should be 10 microseconds before, so we should actually see some separation between those two. Let's bring the time base down. Alright, and on the main sine wave, it actually fires negative and then goes positive. And I bet if I think it said do not change the polarity switch while testing the device. I can't remember if it said that just under certain conditions or under all conditions. So I'm going to turn the test load off, or device under test off. And then I'm going to switch the polarity to negative. And then turn the device under test back on. And yeah, now the pulse fires positive first. Very cool. Let's get back to at a 100 microsecond time base and turn this knob up a bit. Now I'm hearing the clicking. Oh. Something's starting to smell. It doesn't smell like horrible burning, it just smells like electronics that haven't been on for a while and are now turned on. So this smell could get worse. Now is that clipping right there my test setup, or is that what it's actually doing? Maybe it's because we're at 50x. Let me put it at 500x. That's probably the problem. Alright, now we're at 20%, which should be... Oh, yeah. Okay, that was the issue. We just need more headroom on the differential probe. Now this is where the thing started making spicy noises before. And that clicking is getting louder and louder the more I turn this up. So right now we're at, that should be about 800 volts. I don't want to push it all the way to 1,000 just because this is rated for 1,000 volts. And I don't know. I don't want to push it to its limits right now. So that should be 800 volts. And so what do we got? We're at 250 volts per division. So that's 250, 500, 750 on the downswing, and then about 500 volts on the upswing. That's not the correct terminology, I know, but that's the kind of scale we're looking at here. So this is at about 500 volts. This is about negative 750, reference from wherever we are in the main cycle. In fact, let's go... Let's go where we can see the main sine wave. And now... if I twiddle with the phase knob, now we're at 180 degrees. 270 should be at the peak of the sine wave if this thing is accurate. Yep, 270. I'm watching on the monitor, same as you, so when my hand's covering it, I can't even see. But and then that should be, well, close to 360. Yeah, not quite. It's not quite at the trough. And this pot is actually beyond its indication for 360. It's a little bit off there. What if we go down to 0? Yeah, it's still above 0 actually. So we go down to 0. That should be at the trough of the sine wave, right? Anyway, this is neat. 900 volts. But of course, it's more interesting to look at this at a smaller time scale. But yeah. And if we turn it down to 0, we do indeed get no interference at all. Whoa. Huh. I was just fiddling around with the scope, and I heard a click, and I do believe the GFI, I think, tripped. Let me go check. Does this say what the trip current is? Yep, the GFI tripped. Ground fault interrupter, or GFCI, ground fault circuit interrupter, or RCD, residual current device. Whatever your preference for naming conventions is, that's what tripped. So it had some leakage current to ground. Don't know why it would, but something might have arced over internally. The GFI device I have is a plug-in kind, and it says Class A on it. Not sure what trip current it would trip at, but the manual did mention that you should use this with an RCD GFI. Just going to turn it off just in case. And it gave trip current limits, so let me just look that up. Earth leakage currents up to 10 milliamps may occur. And it's saying a protection line should be connected to test object, which I wasn't using a test object per se in this, but I did have the piece of equipment doubly grounded, which I guess isn't what they're saying here, but what I did definitely couldn't hurt. This is what I was looking for. Perfect. Okay. The simulator supply plug, plug 10, that's the one that powers the actual device, not the device under test, may be fitted with a 10 milliamp error current protection switch, or GFI RCD. The test object supply, or the device under test supply, may be fitted with a greater than or equal to 30 milliamp error current protection switch. And so this intimates that you may see earth leakage currents on the device under test side of up to 30 milliamps, but not including 30 milliamps. So the tripping of my GFI may have been normal if mine is set to trip at anything less than 30 milliamps. And as you can see from the time on the scope, it's about 4:13 a.m. here, so I'm going to quit for the night in a moment, but I'm just too curious. I want to see if this device is dead, like this thing like arc over and actually cause a short, a persistent short, or was it just a transient condition? Alright, I'm going to turn on the device. Okay, we got our pulse signal back, so that's good. Device didn't explode, at least internally. And turn on the device under test line. Yep. So we got our mains waveform. And now let's see if we can get... Oh yeah. Okay, it didn't die, it just... Maybe this thing arced over to the earth connection, or we got just some other leakage. Alright, it tripped the GFI RCD, but the device wasn't killed, so that's good. Whee! Fun. Yeah, I mean, this pot seems a little flaky, because it keeps jumping around, so the pot could probably use some cleaning, or at least some twiddling. Okay, so this thing seems to be working. Alright, I'm going to wrap up for tonight, and we'll get back to this tomorrow with some other tests.
Él creyó, no ha causado una
Since the main reason I got this interference simulator in the first place was to test power supplies and also filters, I figured why not get 2 brand new USB power supplies and check them out, see how much, if any, voltage spikes get through to the USB output from the input, and what the isolation is like between the primary and secondary side of the power supplies, mostly to see if, obviously, voltage transients will pass from the primary to the secondary, and even if not in full, how much will that affect the output voltage, and will we see sizable spikes in the output voltage at all? In a good quality power supply, hopefully not, at least not until maybe you approach like 1,000 volts or something, but these are purposefully not high quality power supplies. And these are $4 power supplies, and that's including shipping from Amazon, and these were the cheapest ones I could get relatively quickly. The thing is, over the years, of course, like most people who have a lot of electronic equipment, I've got a bunch of cheap USB power supplies, but I threw them out. If a USB power supply comes with a piece of kit and it's extremely lightweight or has that flimsy hollow feeling, I will generally just throw it straight in the garbage because I don't want to accidentally use it. This one has a surprising amount of weight to it for the cost. This one is USB-C, obviously, and multi-voltage. It claims to do 5, 9, and 12 volts at various amperages, maximum 20 watts. 20 watts in this size, unless this is gallium nitride, I don't know about that, but it might be. I'm not going to do a full teardown on the power supplies. I'll leave that to Diode Gone Wild. I don't want to step on his toes, and it's not my area of expertise anyway.
And what's inside of it? Nice!
Although maybe we'll take a quick peek inside one of them if they fail. This one is USB A and C. The USB-C is capable of 5, 9, and 12, as is the A, and it's 3 amps max at 5 volts if you use them both at the same time. This one does say 20 watts, but 5 volts, 3 amps would be 15 watts. So this one is a bit better packaged. It comes with more wrapping around it. I guess that's good. It's also reasonably heavy. I think I might have accidentally bought 2 halfway decent power supplies, because the ones that I end up throwing in the trash are usually a lot crappier feeling than these. This one's denser. They're probably about the same weight though, which I guess makes sense since they have the same specifications. You figure they should have the same circuitry in them. Well, it does have a power delivery chip in there, I guess, and at least ostensibly it appears to be capable of the voltage that it said it was, so that's cool. First minor problem is it's actually too big to fit into the receptacle because it's a little bit recessed around here. One moment. I'm going to take a wager and say that there's at least a few people watching this that don't know what this is. And if you do know what it is, you might not have one or ever seen one in real life. Back in the day, probably pre-1950s, I don't know the exact time frame, a lot of residential electrical did not have a ground pin. So they were not 3-hole sockets, they were 2-pin sockets. And later on, as grounded household equipment started coming out, well, you couldn't plug it into one of those outlets, so hence this adapter, which, if you don't use it correctly, defeats the ground. It does have this smush down tab. That's smushed down by me over the years. But that tab is supposed to attach to the screw hole in the middle of the receptacle plate, the cover plate, and then that is theoretically grounded. It may or may not be. Yeah, these were used back when I was a kid for all sorts of unsafe electrical hookups. That was back in the day for you. Now, in this case, of course, this is not grounded anyway, so we're not defeating any ground that existed. But now it has a nice long plug. And the reason I chose this is because this way I'm not running a long cord all around the bench with many high voltage spikes on it where it would act as an antenna. So there are safe uses for those adapters. Okay, so here's my test setup. Please ignore everything on the left side because that is a horrible mess, obviously. And that's going to bother a lot of people. And what I have on this side is a male USB-A cable that has been sliced in half and then stripped back. So we have the V negative and V positive, or VCC and ground, depending. It's not really grounded, I don't think. The shield is connected to earth ground, just again for EMI mitigation along this cable, because otherwise this would act as a big antenna. Not that it won't over here where it's exposed, but that's fine. And connected to the voltage out on the USB cable is the differential probe from before. And this differential probe is being monitored by this scope. Then I have another differential probe, this one capable of up to 3,000 volts. And this probe head is just connected to L1 and L2, which again are the same voltage rails that go to this receptacle. And as I pointed to before, this differential probe is connected to the Fluke scope meter. So this is going to be monitoring the input, this is going to be monitoring the output, is essentially what we're doing. And more importantly, the pulse output that corresponds to when there's an interference pulse on the output is connected to the Fluke scope meter, and then there's a splitter splitting off to channel 2 of the Siglent scope. Both scopes, the pulse is on channel 2 and the voltage we're monitoring is on channel 1. Would be nice if I had a floating isolated battery powered scope that had 3 or 4 channels, but hey, kind of have to do it this way for now. And I think I mentioned it before, since I'm using differential probes, I could use a grounded, regular mains powered non-isolated scope. The reason I'm not is because of this piece of equipment being so old and in unknown condition. I mean, it seems to work, but it may develop a fault, and if it, let's say, starts outputting mains voltage on here, I would rather have my scopes isolated. Plus, these two differential probes are very cheap. Well, relatively speaking cheap. They're made by an off-brand company. I don't really know how good MicSig is, but just in case one of these develops an internal fault and is not that isolated at, let's say, 1,000 volts or 3,000 volts, I don't want those spikes going into my good scopes. And so that's the reason for these two scopes being of this type and handheld, battery powered, etc. By the way, I forgot how much of a ripoff of the Fluke scope meter the Siglent is. I mean, when I say ripoff, I guess if you're familiar with the scope meter, it helps them, sell users on this because it's a familiar interface. But it's a very similar interface. Until I saw them side by side, I kind of forgot how similar they were. Fluke does power up faster though, but its display is much dimmer. Okay. And the Fluke does not even have a 500x probe setting. So with 100, we'll just know we have to divide everything by 5, which is kind of stupid, but we kind of know the characteristics of what the interference simulator is outputting, so I think that's fine. Alright, so we'll start with the white one, and that's going to require just because this is the cable I have handy, an A to C adapter, so we can just plug it in there. And yeah, just pop it in there. And just to keep the blue trace away from the red trace, I have the blue trace at negative 15 volts base, which will put it down here, which means we are seeing 5 volts right now on that rail. We're not really concerned with that, we're really just concerned with spikes on that rail that correspond to this downward spike, which is when the interference simulator will fire, and we'll also see the spike on the red trace here. Unfortunately, scope meter channel 1 is red on this one and blue on this one. I probably should have changed those around, but whatever. The point is, red is the mains waveform coming into the USB power supply, blue is the DC output. So it's kind of fitting that those are two different colors, even though it doesn't make sense that this and this are different colors, but because those are the same signal. But whatever. And without getting my hand covering any of this stuff up, which is kind of tricky, bring this up to 20% or so. We can see the spike on the scope meter. I'm going to bring that down a little bit. And as you can see, we got nothing on the USB output. And let me zoom out the timescale a bit just so we can see the entire mains waveform. So you notice we are spiking probably about maybe 75 volts above the peak of the mains waveform. Now I can come in here and change the phase on that. So now that's riding at the height of the waveform. So now we're going 200 volts above peak. And yeah, now we can see there's a tiny little blip there every now and then, but really nothing notable. So depending on the phase, like right now, this spike is not exceeding the peak or trough of the mains waveform at all. So really any device should, I think, be able to handle this kind of spike. Or at least certainly any switch mode power supply should, because that doesn't exceed its voltage rating. And by the way, this power supply should support up to 240 volts in. So really, putting a spike on top of the mains waveform at a relatively low level, as long as it doesn't exceed the peak-to-peak voltage of a 240 volt mains signal. I forgot what the peak mains voltage is on 240 volts, but it's, of course, when you say 240 volts, it's RMS, it's not peak-to-peak. So a reasonable spike here really shouldn't cause a problem with a universal mains input. But let's just bring this down over here and stress it out a little more. I'm going to bring this up to, let's say, 50%, so 500 volts. Oh, okay. We did start seeing something on the Siglent. So now I'm at 300 volts, or thereabouts, or 30% on the output. And then, yeah, once I bring it up like to about 30, anything above 30% really, we start seeing a spike on the output. And then at 50%, we really start seeing a decent spike on the output. But of course, now we have a 500 volt peak. 1, 2, 3, 4, and 5. Yeah, so thereabouts 500 volts. And let's crank this baby up to 800 volts, or thereabouts. Yeah, you can see that's letting quite a lot through to any device that you would have connected to this USB power supply. And let's bring it all the way up to 1,000 just for fun. And I'll keep my hands and arm away from the ends of the USB power supply output, so I'm going to come around here and we'll bring it up to 1,000. Yeah, now we can see we're getting spikes of about 15 volts, maybe, and some transients that are even higher. But they are very brief. Let me just change the trigger on that. Now we're at the same time scale, 5 microseconds per division on both of them. So it's letting a decent sized spike through, going back up to 1,000 volts. Yeehaw. And at 1,000 volts, yeah, we're seeing a spike of about 25 volts positive and down around maybe 5 volts negative. Because our 0 volts is right here, one division below. It is still outputting 5 volts. It didn't kill the power supply, and it didn't blow out the capacitor between the primary and secondary, assuming such a capacitor exists. So at least we're not seeing mains now coming out on the output. And I'll bring it back down. So yeah, we lose that just when we hit about 350 volts, which is probably around peak 240 volts mains. So that would make sense. And now let's bring it up to the peak of the mains waveform. So yeah, we're at about 350 volts. So yeah, if it's riding right there in the mains waveform, it's not peaking high enough. But if we bring it to right at the peak of mains, then yeah, we do start seeing it on the output, which does make sense. And now what if I bring it up to 1,000 volts, because now that's really going to be the maximum I want to apply to this right now. All right, but you can see it's still outputting a stable 5 volts, which is pretty nice. Let's see if there's any larger scale ripple to it. No. So it doesn't look like it destroyed the power supply, at least. That's nice. Ooh. The power supply is quite warm, though. Like, I mean, quite warm. I wonder... now I do kind of want to open up and see what components inside of it are getting that hot, because it's under 0 load. Whatever it is, it's something right on the top here, because that's the hottest part. I mean, it's not hot, but it's warmer than you'd expect. Okay, now for this guy, bring this phase angle back down, so we should have our spike sort of towards the middle of the mains waveform. Just adjust that. Then let's bring this up slowly. Oh, wow. Okay, this one's getting a spike on the output right away at 200 volts at the middle of the waveform. Like, that's odd, because you can see here we're barely exceeding the peak of the mains waveform, which I think is actually doesn't look very smooth. I think the probe is maybe a little out of calibration. This probe is brand new. I haven't really played with it yet, but really we just want to get an idea here. We're really interested in this right now, so that's fine. I know the probe on this one is good. It's zeroed and calibrated as best as possible, so we should be fine there. But yeah, so anyway, at just about 200 volts, or 20%, we are seeing a spike on the output, and it's only getting slight. I think anything above the mains waveform on this one comes through on the output. Yeah, so you can see when we're even with the peak of the mains, we're not really seeing anything here. But as soon as I get above the peak of the mains, and then it just climbs up like in step with it. So let's take it up to, well, at 500 volts, we're seeing about 5 volts positive and maybe like negative 2.5 volts. Let's bring it up to 800 volts. Oh, wow. So now we're spiking And so now we're spiking about 20 volts on the positive side, and I'm just going to center this. And we're seeing, so yeah, we're seeing about maybe up to 20 volts almost positive, and it's almost hitting 10 volts negative. Let's bring it up to 1,000. So yeah, this one performs way worse. This lets way more in the transients through. And now we're going to like negative 10 volts and positive 25 volts almost. So this blue one is performing way worse. Uh-oh. Huh. Well, that can't be good. So I have almost entirely LED lighting around here in the studio, and a lot of it. Absolutely none of this was flickering, but in a little nook under the stairs, way back there, there's a light bulb. And that's LED. And when I crank this up, oh, now it's not flickering. It was flickering in step with the interference simulator activations just before. And I didn't notice it at first because that's the only thing that was flickering. And I don't know if that's because it was, I mean, that's got to be a good 5 meters away from me. So I don't know if it was picking up the interference like spark gap radio wise, or whether it was back propagating through the mains. But of course now it's not flickering. So as soon as I point a camera at it, it cooperates. No, of course now I can't get it to do it. I mean, in the manual for the interference simulator, they do talk about building a Faraday cage around it. I obviously have not done that, and, you know, down here, that's probably not the wisest thing. And I just realized, as far as the phase angle of this goes, we're still, like, riding the middle of the waveform. So let me bring it up to the peak of the waveform. And then we'll whack the full 1,000 volts across it. It's not really going higher, but it does look like the transient is lasting longer. Yeah, that's looking a little thicker at 10 microseconds per division. I did change the scale down to 5 microseconds at one point. But, once again, this power supply at least did not die. It is getting quite warm right here. That is, just for my future reference, next to the ETL logo on that side of the power supply, next to the USB Type A. Right here. It's getting super hot. Now that could just be the inrush resistor or fusible resistor. Might be the same on both power supplies. So I kind of have to open these up now just to see where they're getting hot. Before getting to those USB power supplies and opening them up, let's look at something that was literally collecting dust. Basically since I did a video about it quite a few years ago. And this is the W3900 high-end, spelled H-I, audio grade noise filter. And you can see here it says filters digital noise 2 megahertz to 100 megahertz, restrain interference above 1 kilohertz, which is not what this interference simulator is capable of outputting. But on the Amazon listing when I bought it, it did also say surge and spike protection. So let's put some spikes into it and see how it deals with that. Because I think this thing is mostly BS. I remember, it's been a while since I made that video, but I remember the internals being quite questionable. It was basically, I think, just like a couple of capacitors. Maybe an inductor, I don't remember. But the video is available for you to peruse at your leisure. It doesn't really matter right now. Right now we just want to see if this thing can handle spikes. So I got a purple power inlet cable going to this. That's going to be off screen for the time being. But talk about EMI, I mean. And then it says that the black outputs are direct and the red outlets are filtered. So the black ones will just let through the transients, but the red ones should not. So plug this little guy into there and plug the differential probe quite simply into there. And you know what, just for belt and suspenders sake, let's throw an extra ground between that and the interference simulator, just to make sure we have an earth ground to this power strip, or whatever you want to call it. So now we're just monitoring mains here, and yeah, it doesn't really look like it's filtering anything out. Let's get the same scale on both scopes. that is looking very similar. And on both these, we're at 100 volts per division because, again, remember, this says 20 volts, but that's multiplied by 5. So this is 100 volts per division. This is 100 volts per division. Yeah, call it 2.5 divisions. So we're seeing about 250 volts on the peak of this spike and about 250 volts on the peak of this one. So this noise filter isn't doing anything to suppress transients. Not hugely informative, but it is pretty much what I expected. There is really no spike protection in this device. That was a lie on the Amazon listing. I've been waiting, I think, like 6 years, maybe more, to test this. I purchased the interference simulator shortly after purchasing this device, planning on making a follow-up video about it, but then I just didn't care enough, and this thing sat in my basement for years. And I finally got around to using it because I do want to use it to test power supplies, which I had a video, I think 2 or 3 videos ago, where I tested a high amperage USB power supply, which also had an XT60 connector. And I did not use this interference tester on it because I hadn't deployed this yet or even played around with it. But also kind of the, not irony, but like the risk involved in using this device to test a power supply is that it could be a destructive test. So yeah, I mean, since these were so cheap, I really don't mind destroying them right now. Oh yeah. Whoa! Never seen one fly off like that. Okay, that went across the room. But liberated. Alright, and I said it was hot on the side of the USB-A connector, which would have been like that towards the mains input. And that would have put it like this capacitor right here getting hot, which is rated for 400 volts. So I'm guessing, yeah, this capacitor... Oh, it's actually 2 capacitors in parallel. So actually, that's not too bad. It's got 2 main smoothing capacitors, 15 microfarads, 400 volts, which is an appropriate rating, although the smoothing capacitor on the output side looks a little chintzy. 16 volts, 680 microfarads, and by the looks of it, this does not have separate voltage control for both of these ports. Therefore, if this USB-C port demands 12 volts, then you'll get 12 volts out on the USB-A, because there's no independent voltage regulation here between the 2 ports. We got the optocoupler. Yeah, we do have a class... Is it a class X1 or Y1 capacitor? Yeah, let me take a picture of the capacitor's markings up close. If I can get in there. And get enough light in there. Yeah, class Y1. And I'm not going to... Like I said, if you haven't seen Diode Gone Wild's channel, I'll link it in the description. I really like it. He's done a series of videos where he tears down USB power supplies like this. Usually cheap ones, although some quality ones. This one, I mean, just based on the appearance, looks like it errs more on the side of quality. Like, I'm surprised this was $4 with shipping. Yeah, and it does look like the transformer has a safety winding on the secondary. Like, in other words, like probably a double insulated secondary. And the pins for the secondary, the wires actually come out and go to this separate piece of plastic here. And then the taps are there and there. And this has good separation between the primary and secondary. Yeah, all told, I mean, I would say not dodgy, or whatever he does.
Slightly dodgy.
This one I'm not getting the good crunchiness. Oh, wait, there we go. Haha. Oh, this one actually has a bunch... Oh, that's why it didn't come out easily. It's got a whole bunch of potting compound style goop in there. And it's a 3D chessboard. That is a compact little power supply. Wow. This does not look like it would be great for heat dissipation. I mean, it's got this goop, which I'm guessing should be thermally conductive, but it's not evenly applied or well applied, and it doesn't really mate with the outside of this case. So really all you're doing is sinking heat from like the diodes and the transformer into the capacitors, which is not good. And I said this was emitting heat on the top, I had said. So that would be, and the top was where the lettering was. So I was saying that it got hot right here. And right there, this is again probably the mains filter capacitor. So that's probably what was getting hot. I doubt it was the transformer, which is also right there. The transformer does look like it has a double insulated secondary, and it is the safety type where the secondary is stripped back only far away from the transformer core, or transformer windings. You know what? Like I said, not my area of expertise. If Diode Gone Wild ever happens to watch this video or anyone knows him, tell him I will send these to him free of charge if he wants to check them out on his channel for whatever reason. No pressure though. I don't care one way or the other, but the goal of this video is not for me to really test these power supplies other than for voltage spike pass-through. But yeah, I'd leave the rest of it to the professionals, as it were. This one I'm less enthusiastic about because it's basically this. It's got the same specs or similar specs to this power supply, but you're cramming it all into a smaller volume, where it's going to be much harder to dissipate heat out of these components and keep heat away, particularly from the electrolytic capacitors. Yeah, so this just seems a little too small for its own good, a little too crammed in there. I don't know about the primary and secondary separation, but this guy actually seems halfway decent. But anyway, that was a complete tangent, but that's what's in those USB power supplies. Higher quality than I thought. I was actually hoping for really crappy ones, but they did let a decent amount of transient through. It seemed like pretty much anything that swung above the max peak-to-peak voltage of 240 volts RMS went through on this one, and anything above the peak voltage at 120 volts RMS went through this one. What we are going to do in the next step of this video is check out the module in more detail, because we looked at the schematic and the basics of the mainframe itself, which is really just mains voltage filtering. There's not too much interesting in there, but the more interesting stuff should be on this side of the machine where the module plugs in. Let's look at the module in some more detail, as I already said. Maha!
Continued in part 2.